Hello, everyone. My name is Henry Burton, and I'm Associate Professor and the Presidential Chair in Structural Engineering at UCLA. In this video, I will give a brief synopsis of a paper that I worked on with Jack Baker, who is a professor in the Civil and Environmental Engineering Department at Stanford University. The focus of the paper is on using causal inference principles and methods to evaluate the effectiveness of ground motion intensity measures. The paper was recently published online in Earthquake Engineering and Structural Dynamics, which is the journal of the International Association of Earthquake Engineering. As a quick side note, the study is part of a larger effort of our group at UCLA to advocate for the use of causal inference principles and methods in earthquake engineering more broadly. This paper, which was published in Earthquake Spectra, discusses the opportunities and challenges in our field for implementing causal inference on observational data. There's a long history of studies on evaluating the effectiveness of different ground motion intensity measures, or IMs, for use in nonlinear response history analyses in the context of performance-based earthquake engineering. The earliest of these studies date back to the late 1990s and early 2000s. There are several different criteria that are used to evaluate IM effectiveness. One of the most popular is efficiency, which is based on the dispersion in the engineering demand parameters, or EDPs, generated during nonlinear response history analysis. The basic idea is that an efficient IM is one that minimizes the dispersion in the EDPs. The sufficiency criterion is also one that is often used along with efficiency. We say that sufficient IM is one that produces EDPs that are independent of the upstream parameters used in ground motion models after conditioning on that IM. These upstream parameters are things like the earthquake magnitude and source to site distance. There are other criteria such as scaling robustness and practicality, which, while not as popular as sufficiency and efficiency, are sometimes used. In this paper, we introduce an approach to evaluating IMs that leverages the principles and methods from causal inference. The approach actually tries to address the conditional independence problem that is considered in the sufficiency criterion. So in that case, it can be considered as an alternative to the sufficiency-based approach. The next couple of slides are just going to give an overview of the basic setup of the causal inference problem. This figure shows a directed acyclic graph, or DAG, which is used to show the causal relationships between the variables that are considered. The first variable is the IM, which in the language of causal inference is defined as the treatment. There's also the EDP, which again, using causal inference language, is the outcome variable. There's also the vector X, which represents the set of upstream parameters. In this study, the earthquake magnitude and source to site distance are the two considered upstream parameters. There are also these U variables, which represent the unmeasured variables or variables deemed unimportant for the causal assessment. We are essentially showing them for completeness, and there are some specific criteria that these unmeasured variables should meet, which are discussed in detail in the paper. In terms of the causal relationships, we are primarily interested in the influence of the upstream parameters on the EDPs, and we conceptualize that influence as having two parts. The first part is mediated by the IM. In other words, that part of the effect of the upstream parameter on the EDP flows through the IM. The other part flows directly from the upstream parameter to the EDP. And we say that the most desirable IM is the one that maximizes the part that flows through that IM as opposed to going directly to the EDP. I said earlier that the causal inference approach tackles the same conditional independence issue as sufficiency. Well, in that sense, you can think of this conditional independence as having the phi in the DAG being equal to 0, or all of the effect of the upstream parameter on the EDP flowing through the IM. To solve the causal inference problem, we use the double machine learning approach, which was developed by Chernozyakov et al. This figure just gives an overview of that approach. Once you have generated your data set of EDPs using nonlinear response tree analyses, you start by randomly splitting that data set into a main part and an auxiliary part. Using the auxiliary part, you generate two estimators. The first uses the upstream parameters, M and R in this case, to estimate the EDPs, and this is done using a machine learning model. We use random forest for this. The other estimator predicts the IM as a function of the upstream parameters. The last step is to regress the residuals from these two estimators against each other, and the coefficient from this regression is the causal effect theta. This slide summarizes some of the results from the causal inference-based evaluation for peak story drift ratio, or PSDR. It shows the results for 4 buildings ranging from 5 to 19 stories. The horizontal axis in the plots represent the causal effect computed using the double machine learning, and the vertical axis is the story number. There are 2 types of causal effect calculations. The first is based on the maximum of the peak response over the height, which is shown using the squares at the top of the plot. The second is the causal effect for the full profile response. There are 2 main takeaways here. First, the results are consistent with prior IM evaluation studies, where we are seeing that PGA generally has the lowest causal effect or is the worst IM for PSDR, and SA average and PGV are the best. The second is that the findings based on the maximum response over the height and full profile response are generally consistent. This is important for 2 reasons. As we detail in the paper, this is not always the case for this efficiency and sufficiency-based assessment. Also, in most prior studies involving efficiency and sufficiency, only the maximum response over the height is considered. This slide shows similar results for peak flow acceleration, or PFA. The observations from the previous slide also apply here. For example, PGA is generally the best IM, and this is the case for both the maximum and full profile peak response. We also performed efficiency and sufficiency-based assessments. This slide just shows some results for sufficiency with respect to magnitude for peak story drift ratio. The 2 main takeaways are that the findings based on the full profile and maximum response are different. Remember, we said for the causal inference-based evaluation, these two types of results were consistent. The second finding is that there's no consistent trend that can be linked back to structural dynamics principles. One of the things we noticed in this study is that the findings from the sufficiency-based assessment were not really consistent with prior studies. However, we also realized that most prior studies used on the order of 30 to 50 ground motions, whereas in this one, we actually used 240 records. Therefore, we wanted to know if the findings from the 3 types of assessment, efficiency, sufficiency, and causal inference, are affected by the number of ground motions considered. We use sampling with replacement to repeat the 3 types of assessments for 40 through 240 ground motions at an increment of 40. This table shows the results from the causal inference-based assessment for peak story drift ratio in a 19-story building. It shows that the results are invariant to the number of ground motion. In other words, the best IM from a causal perspective does not vary with the number of ground motions. We saw the same finding for efficiency, meaning the most efficient IM did not change with the number of considered records. However, for sufficiency, we saw a general reduction in the p-values for larger numbers of records, which is consistent with statistical principles. Also, some IMs were not sufficient when we use 240 records, but were sufficient when you get down to 80 or 40 ground motions. In other words, the sufficiency results are not invariant to the number of ground motions used in the analysis. That was just a quick summary of the overall approach and key findings in the paper. Obviously, this is covered in much more detail in the actual paper, which can be found using this citation. We'd be happy to get your feedback on the paper, which you can leave in the YouTube comments.